Hello everyone, my name is Loïc Ferreira from Orange Labs. In this presentation we'll talk about the Sigfox technology and describe several flaws that harm the system. The outline of the presentation is the following. First, we will introduce the context Sigfox is taking place. Then we will explain the security mechanisms used in Sigfox. We will continue with new flaws and attacks against Sigfox. And finally, we will conclude. Sigfox is a technology used in the Internet of Things, which is similar in some way to LoRaWAN or NB-IoT. More precisely, this technology allows a remote end device to communicate with the backend network through several kilometers, up to 50 kilometers in countryside and much less in a urban area. The rate is rather low, only hundreds of bits per second, and the messages are also quite small, only a few bytes. Sigfox networks are deployed worldwide, and at the time of writing the final version of the paper, they are deployed in 72 countries, covering 1.3 billion people, and every day 56 million messages are sent by 17 million remote end devices. Typical use cases include asset tracking, geolocation, monitoring sensitive sites in order to detect intrusion. Sigfox end devices are also used to interact with other equipment in smart homes, such as lighting, heating, and others. Sigfox is used to collect measurements, such as electricity, water consumption, for instance. It can also be used to interact with medical devices that are implanted inside the human body. The tunnel established with the medical device with Sigfox allows retrieving data from that equipment or sending commands to this equipment. Therefore, the Sigfox protocol must guarantee a higher security level due to its sensitive usage. A typical Sigfox network is made of remote end devices, on the left in this picture, that communicate with gateways through a radio link. The gateways are connected to a central cloud. The messages received from the end devices by the cloud are transmitted to the service provider, which is the owner of the end devices. Conversely, the service provider can send messages to its end devices through the intermediary of the cloud. Sigfox manages the cloud and the gateways, whereas the end devices are deployed by their owner, the service provider. Sigfox proposes different types of subscription, which differ on the number of messages an end device can send on a daily basis. The cheapest subscription allows sending at most 2 messages per day, and the most expensive, which in fact is not that expensive, allows sending up to 140 messages every day. Now we are going to present the security mechanisms used in Sigfox. So security is based on a static key called network access key. Each end device shares a distinct NAC key with the cloud. The latter stores the NAC keys corresponding to all Sigfox end devices. The 128-bit NAC key is used during the lifespan of the end device. It is never changed and there is no session key derivation whatsoever. Sigfox provides two security properties: data authenticity, which is mandatory, and data confidentiality, which is optional. These properties, guaranteed by Sigfox, aim at protecting the radio interface, that is, the messages exchanged in the uplink and downlink directions between the remote end device and the Sigfox cloud. Other security mechanisms are also used between the cloud and the service providers, such as TLS, for instance. But this presentation focuses on how the radio interface is protected. With the NAC key, the end device computes an uplink frame as follows. The data carried in an uplink frame ranges from 1 to 12 bytes. In that case, the data takes place in the payload field. The data can also be 1 bit long and is then included in the header field. The header contains, among other parameters, the end device's identifier and a counter which size is 12 bits at most. The counter is incremented every time an uplink frame is sent. The size of the MAC tag ranges from 2 to 5 bytes, depending on the size of the payload. The MAC tag is computed over the header and the payload, which contains the clear data in that case. The key used to compute the MAC tag is the static NAC key. Optionally, data can be encrypted. In that case, the computation of the MAC tag is slightly different. First, the payload contains then the encrypted data. Secondly, the input to the MAC computation is the header, which includes the 12-bit counter, the payload, but also an 8-bit implicit counter called RC in this slide. This counter is not transmitted in the frame, contrary to the explicit 12-bit counter. This implicit counter allows extending the anti-replay mechanism to 20 bits instead of at most 12 bits when data is not encrypted. A downlink frame is computed in a similar way. The data transported in a downlink frame is always 8 byte long and the MAC tag is always 2 byte long. The payload field may carry clear or encrypted data. The computation of the MAC tag with the end-device's NAC key involves the end-device's identifier and the 12-bit counter, which are transmitted in the corresponding uplink frame, and the payload, which contains either the clear data or the encrypted data. As we can see, the anti-replay mechanism for a downlink frame depends only on at most 12 bits. The Sigfox MAC function is based on AES in CBC MAC mode. Therefore, in order to get an input to the CBC MAC routine which size is a multiple of 16 bytes, Sigfox applies a non-standard padding scheme. The input data is concatenated to itself until the proper size is reached. Then this intermediary byte string feeds the CBC MAC routine, and the output is truncated in order to have a MAC tag which size ranges from 2 to 5 bytes. The same holds regarding a downlink frame. Starting from a clear frame or an encrypted frame, the first bytes are appended to the frame in order to get a 16-byte block. The output yielded by the CBC MAC calculation is then truncated to 2 bytes. Encryption is done with AES in counter mode. For a given end device, the encryption key is always the same and is computed from the NAC key. The byte string used to build the counter vector depends essentially on the 8-bit implicit counter RC and on the 12-bit explicit counter. We stress that this description is not official. To the best of our knowledge, there is no official Sigfox document specifying the encryption function. This description comes from Pinol's blog, and we have correct Pinol's description with reverse engineering. Finally, the result that we have obtained has been confirmed with practical experiments that we have made with the personal end device in interaction with the Sigfox cloud. These experiments confirm that uplink frames and downlink frames are indeed encrypted as explained in this slide. Now we are going to present several new flows and attacks against the Sigfox protocol. The first issue is related to the way data is encrypted in an uplink frame. As said, data can be transported either in the payload field or in the header when it is 1 bit long. We have observed that when encryption is activated and data takes place in a header, data is in fact not encrypted. The fact that a single bit be not encrypted may appear as not very significant. However, according to us, one should not presume which purpose the final user intends to achieve with a security mechanism. If a security protocol claims to provide some property, and in that case confidentiality, it must ensure the latter. And here, Sigfox did not achieve the intended security level. That being said, it is unclear to us whether the lack of encryption in a single bit case is a choice or a bug. It may be possible that computing 128 bits in order to encrypt a single bit is deemed too energy costly. On the other hand, it is also possible that the encryption function reads the data to be encrypted in the payload field, which would yield nothing when this field is empty. The second flaw is related to the anti-replay mechanism. Per specification, the explicit counter, which is 12-bit long at most, must be reset to 0 when it reaches its highest value. With the Platinum subscription, an end device can send 140 uplink frames per day. This means that the counter wraps around every month roughly. Since the same NAC key for a given end device is used to compute the MAC tag of all frames, this means that every month all previous uplink frames become cryptographically valid anew. This observation regarding the frame counter is in fact already known, but in addition we can add that the downlink frames can also be replayed, since they are computed based on the uplink frames counter. In order to thwart the frame replay, Sigfox advises to apply encryption. And indeed, when encryption is activated, the uplink frame depends on a 20-bit counter instead of 12 bits at most when the frame is not encrypted. These 20 bits correspond to the 8-bit implicit counter and to the 12-bit explicit counter. However, the downlink frame depends only on the 12-bit explicit counter even when encryption is activated. Therefore, a previous downlink frame can be replayed when the 12-bit explicit counter rolls over, even if encryption is activated. This contradicts the argument raised by Sigfox. Moreover, a clear downlink frame is indistinguishable from an encrypted downlink frame. The only difference is that encrypted data takes place in the payload field instead of clear data. So, let us imagine that an end device sends encrypted uplink frames, receives encrypted downlink frames, and up to some point deactivates encryption. The end device expects now clear downlink frames. If the counter rolls over, then previous encrypted downlink frames can be replayed by an adversary to the end device. The end device will accept these frames since their MAC tag becomes valid anew. Moreover, since the end device expects clear data, it will take the byte string carried in the payload field and send it to the application layer. However, the content of the payload field in that case is encrypted, hence corresponds essentially to random stuff. To that point, what happens next depends on the application layer. However, this may harm the end device and put it in an incoherent state. The last flaw that we will raise is related to the way a MAC tag is computed, and more specifically, to the padding scheme used in the Sigfox MAC function. Let us consider a message M made of 7 bytes, B0, B1, B2, etc., up to B6. In order to compute a MAC tag for this message, the Sigfox padding scheme is applied, which means that the input is concatenated to itself. In this case, the padding function yields B0, B1, etc. up to B6, followed again by B0, B1, etc. B6, finally followed by B0 and B1. These 16 bytes are the input to the CBC MAC routine, together with the end device's NAC key. Now let us consider a different message, M', which is equal to M concatenated to itself. Applying the Sigfox padding scheme to M' yields the same intermediary byte string as for M, that is, the same 16 bytes. Since the inputs to the CBC MAC routine are the same as previously, the output, that is the MAC tag for M', is the same as the MAC tag for M. This means that two different messages M and M' do have the same MAC tag. Concretely, let M be a genuine message sent by a legitimate end device. An adversary can trivially forge a message M' from the genuine message M, and the adversary knows that the MAC tag for M' is the same as for M. In practice, the adversary has two possibilities. First, she can eavesdrop on a new frame and forbid that frame from reaching the cloud. In that case, she can use a clear or an encrypted frame. Secondly, she can replay a previous frame when the explicit counter is reset to 0. And in that case, the adversary can only use a clear frame. Even though such an existential forgery does not require any computation power, not all legitimate frames can be used. Indeed, the size of the MAC tag and the value of some flags in the frame's header depend on the payload size. For instance, a frame carrying a 1-byte data has a 2-byte MAC tag, and flags in the header are equal to 0, 0. It cannot be used to forge a frame corresponding to, say, 3-byte data, because the flags in that case are different, they are equal to 0, 1, and the size of the MAC tag is also equal to 3 bytes. Nonetheless, a lot of forgeries are still doable with clear and encrypted genuine uplink frames. For instance, if one considers a clear frame transporting a 1-byte data, one gets a valid forged frame by merely concatenating to the original payload the header followed by the payload again. Likewise, from a genuine encrypted frame containing a 1-byte payload, it is possible to forge a valid encrypted frame by concatenating to the original payload the implicit counter followed by the header. And then this yields a valid encrypted frame which payload is 8 bytes long. All these forgeries that we have described have been validated. First, we have made an offline verification with an open source code that we have completed to add encryption. Secondly, we have made practical experiments in real life with our personal end device and in interaction with the Sigfox cloud. And all the forged frames have been accepted by the cloud as valid frames. The countermeasures are straightforward and efficient in terms of computation. In order to mitigate the first flaw related to the lack of encryption in the single-bit case, it is enough to apply encryption as when the payload is present in the uplink frame. Regarding the frame replay, this can be prevented by including in the MAC computation the implicit 8-bit counter as it is done to compute an encrypted uplink frame. This implicit counter must be involved in the MAC computation in all cases, when encryption is activated or not, for uplink and downlink frames. If the 12-bit explicit counter rolls over after 1 month, in the best case for the attacker, it is unlikely that this extended 20-bit counter will roll over, since 256 months likely exceeds the expected lifetime of an end device. Finally, the existential forgeries that we have described can be thwarted by replacing the CBCMAC mode with the CMAC mode, which is secure for variable length inputs. Moreover, CMAC is based on the same inner operation as CBCMAC. Therefore, this change does not imply any additional computation cost. During this work, we have responsibly disclosed our findings. As soon as our observations were validated with practical experiments, we have shared with Sigfox our results. Sigfox did acknowledge receipt of our paper, but did not send further messages. And at the time of presenting this work, and despite new messages sent to Sigfox, we have received no response from the company. To summarize, we have made an extensive analysis of the Sigfox protocol, which is worldwide deployed. Sigfox mandates only one security property, data authenticity. We have presented a comprehensive description of the security mechanisms used in Sigfox. We have extended previous attacks, and we refer the interested audience to the full version of our paper. We have also presented new flaws and attacks against Sigfox, the main one being the ability to make existential forgeries from clear or encrypted uplink frames. This attack breaks the only security property that is mandatory in Sigfox, which is data authenticity. These attacks have been validated experimentally. And finally, we have also described efficient countermeasures. To conclude, we can observe that the theoretical principle of these vulnerabilities is in fact well known to the practitioners and to the cryptographic community. Very likely, according to us, more openness while designing these security mechanisms in Sigfox would have prevented these flaws. Thank you for your attention.